In this video, we'll create basic 3D geometrical shapes like cone, cuboid, sphere, etc. using scribble3d.com. Open the 3D editor page. We'll now create and upload an SVG file to make a 3D model of a cone. Open Inkscape. First, we draw the cross-section of the cone, which is a circle. Next, we draw a vertical line, which is the path along which the cross-section is extruded. We call the cross-section as the slice, and the extrusion path as the spine path. Now we draw the side view of the cone, which is a triangle. We call this side view as the silhouette path. Draw a vertical line intersecting the silhouette path. We call this vertical line as the width line. We'll see later in the video why this width line is needed. Draw a rough line that encloses the spine path. This is the spine range. Draw a line to intersect the slice with the spine range, and another line to intersect the spine range with the silhouette path. To mark the vertical line as the spine path, change its stroke color to blue. Save this SVG file. In the web page, open the newly created SVG file. Click Next. In the top right section, the spine diagram is displayed in a tree structure. Clicking on the nodes of the tree shows the labeled components of the spine diagram on the left. The orange line is the spine range. The dashed lines are lines associating the spine range to slice or silhouette. The brown-colored triangle is the silhouette path, and the vertical purple line is the width line. The length and thickness of the model can be adjusted. For 3D shapes that have pointed ends, set the flag Allow 0 width for a more accurate shape. Save the file in the cloud. I'll briefly explain how this diagram is interpreted as a cone. The blue-colored spine path is the path of extrusion. Imagine the cross-sections to be rotated perpendicular to the spine path in 3D space. Place multiple cross-sections on various points along the path. The next step is to extract the width data from the silhouette path and the width line. Width is extracted by lines drawn perpendicular to the width line, intersecting the silhouette. Now scale the cross-sectional slices proportionately, corresponding to the extracted width at each point. Scale the bottom slice, scale the middle slice, scale the top slice to 0, as the width extracted at the first point is 0. Joining the edges of the slices in 3D space will create a surface corresponding to a cone. Adding more points along the spine path will create a higher resolution mesh for the cone. So this is how the 3D model of the cone was generated from the diagram. Some sample SVG data is provided in the drop-down list. We'll use it to create some basic shapes. This diagram creates a cylinder. This diagram creates a cuboid. If this square is replaced by a hexagon, the hexagonal slice will be extruded. See the updated geometry. This diagram creates a cone, as we saw earlier. This diagram generates a cube. To create a cube, the length of the spine matches the height of the slice. This diagram creates a sphere as output. To fix the flattened ends, set the flag Allow Zero Width. Increasing the segments creates a higher resolution sphere, which is smoother. This diagram creates a hemisphere. Adjust resolution if desired. This diagram creates a pyramid-shaped object. As usual, the attributes are adjustable. This diagram creates a torus. The small circle is the slice that is extruded along the bigger circular path. The resolution is adjustable. The model created here is a triangular prism. Here, the string spine.vars is placed near the blue spine path, so the name vars will be assigned to the generated object automatically. You can see that the object has been given the name vars. If we replace the circular splice with a pentagon, the 3D shape changes accordingly. This diagram will create a 3D model of a banana. To understand how the diagram generates a banana model, let us open the SVG file. This cross-sectional slice is extruded along the blue-coloured spine path. Imagine this slice to be rotated in 3D and placed at various points along the spine path. Rotate each slice so it is always perpendicular to the spine path in a 3-dimensional space. Use the silhouette for width extraction. I've removed the other lines for clarity. Now scale each slice proportional to the width of the silhouette at that point. Join the edges of the slices and we get the 3D surface. This is another example of generating banana model. The width extraction is done perpendicular to the vertical line here. For a brief description of how this diagram generates a banana, let us download and look at the SVG file. The idea is similar here. The slices are placed and rotated along the blue-coloured spine path in 3D space. The next step is to extract the width from the silhouette. Width is extracted by drawing lines perpendicular to the vertical line. Calculate the length of the line between the intersection points. Using this width data, the slices are proportionately scaled at the corresponding places. The top and bottom slices are smaller, so they are scaled down. The more segments along the path, the more the resolution. So that was an attempt to explain how this diagram generates the 3D model of a banana. This diagram generates a 3D model of a baseball bat. The width is extracted along this vertical width line. This is a slightly more complex shape. It contains 3 spine diagrams. The text embedded in the diagram will be used to assign names automatically. The first 3D model created is a simple bottle with a circular cross-section. The second bottle contains circular cross-section at the top and a square cross-section at the bottom. Highlight the slices to locate them in the spine diagram. The third bottle also has circular slices at the top and square slices at the bottom. However, for this section of the spine path, the cross-section values are interpolated smoothly along this length. So, there is a gradual transition from a circular cross-section to a square cross-section.